Hello everyone. Welcome to Module 8 for Data 609. We focus on artificial neural networks and deep learning. As the course progress, as you can see that at this stage, we are actually at the final stage of the algorithms that we're interested in discussing. So let's take a look at artificial neural networks and deep learning. First of all, you know that there are multiple types of learning algorithms. One of them is called supervised learning. The other type is called unsupervised learning. You probably are aware that supervised learning would be use the data with known labels and classes. So regression itself is one type of supervised learning, and classification would be supervised learning as well. For unsupervised learning, essentially the data doesn't have a label. In other words, there is no Y variable that's actually being observed. Then you would leverage clustering methodology, and that is a classic example of unsupervised learning. And in terms of neural networks that we are going to discuss in this section, it can be supervised, can also be unsupervised. If we're training on the labeled data, then we call it supervised learning. If we're training on unlabeled data, then we call it unsupervised learning. And then there are all kinds of other types of learning method or categories. So you should be aware, including reinforced learning and semi-supervised learning and other types of learning as well. You should read the trends in deep learning in this chapter so that you can get a better understanding of what other learning algorithms or learning categories are available out there. But majority of the time, we focus on our study and learning in the supervised learning and unsupervised learning space. Let's take a look at one example for neural networks, but let's start with something called neuron model. So neuron model started in developed by McCullough and Peets in 1943. And then the method itself, it says that if you have a bunch of input, let's look at the chart on the bottom left-hand side, that is U1, U2, etc., UI, etc. And then what you can do is with all this input, you have a bunch of weights corresponding each link, then W1, W2, WI all the way, etc. And then you can use summation of UI times WI to get a X value. Here X is summation of UI, WI, and the majority of the time, what we do is the output is a function of this X. So oftentimes people actually have, let me get a pen. Oftentimes people actually have something called activation function that is after the summation. So in other words, the activation function is taking this form of fx. Fx is something that we don't know. So first of all, what we do is we have a summation of that and then take a fx to come back with our y. This fx itself is called activation function. And then if you use an example on the right-hand side that says, often with a threshold of the parameter, for example, on the right-hand side, what it has is it's binary. If x is larger than equal to theta, then it's 1. Otherwise, it's 0. Essentially, you can see that anything that's larger than this would be theta, would be 1. And then anything less than here would be 0. And then we essentially call this point as the theta threshold. And then if you look at this smooth activation function of sigma function, Sx is really this red line that is approaching 1 and 0 as well. It's 1 over 1 plus exponential of negative x. This is called the neuron model. Now let's look at a special case of activation model that we just discussed. If it's taking that 1 over 1 plus exponential negative x, this sigma function, it has a very unique property that is s prime x turns out to be sx times 1 minus sx. The good property is really that in order to take the first order derivative, you don't really need to take the first order derivative. You are able to use original function and then use that function times 1 minus the original function comes back with this first order derivative. So that property essentially helps you to simplify a lot of calculations. Now, there are other types of activation function with different activation behavior as well. For example, let's look at the first one. First one calls rectified linear model or rectified linear unit. It's called ReLU. So it's widely used in deep learning. What it does is anything that's larger than x would be x, and anything that's less than x, less than 0 would be 0. So a desired property of ReLU is that its derivative is 1, it's a constant. So if you think about this, let me draw this very quickly. It would look like more like this function form. So at the value of x equal to 0, it is, if this is x, then x equal to 0. Anything larger than 0 is x, and then less than 0 is 0. And then good news is its derivative is a constant of 1. And then a ReLU function can also be approximated by a smoother function called soft plus. And then soft plus is actually shown on next page. We can take a look shortly. And then before we do that, take a look at this parametric rectified linear unit, PRELU. That is, anything that's less than 0 is alpha x, but anything that's larger than 0 is x, meaning less than 0 would be alpha x, which is smaller value alpha, usually is 0.01. So that is the function form. In other words, you have an x. X is a summation of wi, ui, and then you need a function, activation function, to come back with a y output. And then this activation function itself can take different function forms depending on different characteristics of problem set. Okay, let's move on to the next page so that you are able to see what I was talking about in terms of the approximation of the smoothing function of the ReLU. So here, this is the ReLU, which is in the blue line, and then the approximation of log 1 plus e powered by x is really approximation of the ReLU. And then you have exponential linear unit, you have a hyperbolic tangent activation function, and then you also have a softmax activation function. You can see that all of these tend to have different function forms. It really depends on the problems itself. Now you have a good idea on a neuron model. You have a summation of ui, wi, and then it needs an activation function. Now, as you can imagine, in all the software packages, it would embed all of this activation function. And then at the end of the day, what you really need to figure out is which would be the proper activation function I should try. I'm not going to try everything, right? I would try some, but which would be the ones that I can try, okay? That is a neuron model. Let's look at neural networks, artificial neural networks. So a single neuron can only perform a simple task. It's on or off. A complex function can be designed and performed using a network of interconnecting neurons or perceptrons. It's also called neuron. It is also called perceptron. So there are all kinds of network structure exist, but one simple way is something called layered neural network. It does have a one layer, input layer. You can see here which would be all this input. This is called input layer. And then you have an output layer, Y1, Y2, all the way to YK. And in between, there is a hidden layer. In this case, we have 1H all the way to M. Of course, there's a reason that we have this one. It's almost like in linear regression, you have an intercept, which exactly this is the reason that we have this one. In here, I'm not going to get into too much of detail of how we design this network for now, but at least you know we have an input layer, output layer, and a hidden layer. And then what you do is for each hidden layer, you would have a corresponding WII W1 input 1 to the first hidden layer 1, or WI1, the ith input to the first value, first node of the hidden layer. You have all these kind of weights. And then if you can see that more generically, for each hidden layer to output of k, you have W weight HK to come back with a YK. So you have an input layer with Ni inputs, hidden layer with M nodes, and then you have an output K with N output. If you have N observations, correspondingly you have N YIs, and then that would be output. So now this is called artificial neural networks. Now, what interestingly, right, you have to, I need to figure out what's the corresponding weight, what would be my relationship between my input and output. At the end of the day, you have to have some sort of error term that you want to minimize or maximize. Of course, majority of the time, if it's error, we're trying to minimize. Then in this case, what we do is we use VK to stand for the predicted output. And YK is a corresponding observation of the case observation. Then what you do is just YK minus VK squared, summation of every single node, single observation, and then a half. That would be your least square of the error term. Of course, you can show it. You can use L2 norm to represent this as well. And then you can see that if we are going to minimize this error term, again, it's an optimization problem. You can use any proper optimization techniques to find the corresponding weight. However, special techniques such as gradient-based method tend to be more efficient. That's the reason that if you go back to chapter 2, chapter 3, we did discuss gradient-based methods. Now, what it does is, if initially we have WHK, if you go back to the previous page, we use this WHK as an example. If we have WHK for the previous iteration, now we need to update WHK by delta WHK. And then delta WHK is defined as negative eta partial order derivative of error term in terms of this weight. And then it can be further decomposed into the error term, partial order derivative of error term in terms of the VK, predicted value of the K point, VK. The error term in terms of the value, predicted value of VK, and then partial order derivative of VK in terms of WHK. Partial derivative of VK in terms of WHK. So instead of error term partial derivative in terms of WHK becomes error term in terms of VK and then vk in terms of WHK. And now, once you have this HK, then what you do is you get you can always update your W, your weight, so that you can continue to run until the model converges. Now, let's specifically use one example. That's called backpropagation neural network. So essentially says that if it has this layered structure, then what we can do is we can estimate the error from the output layer and backpropagate to estimate the errors of the hidden layers and then to the input layer. This is called backpropagation neural network. And then if you look at this formulation now, in input of the output layer are the nodes of the hidden layer, right? In this case, let's assume it's only one layer, but potentially you have multiple layers, multiple hidden layers, then it becomes a little bit more complicated. And then deep learning is based upon this multi-layer neural networks. So now, for now, you just need to know what is multiple hidden layer neural network, but very quickly you would realize the relationship between multi-hidden layer neural network and deep learning. Now, so let's assume that the input of the output layer would be the nodes. It's not assumed, it's really the case, right? The inputs of the output layer are the nodes of the final hidden layer. That is to see that VH times WHK summation would be my SK. So go back, WHK times VH, WHK times VH, summation of all of them would be my VK. But that VK, the summation is an activation function of FK to get me my summation of the, not VK yet, right? Summation of that, you need the activation to get to my VK. So that is, once you have summation, you need a FSK so that you can get my VK. If we're using sigma activation function, then we know that VK prime is fxy minus fx, so that we know that if we use partial order derivative of VK in terms of WHK, now it becomes partial derivative in terms of SK and SK in terms of W. So we know we can simplify the calculation based on this partial derivative. You can come back with this relationship. And then we know that a partial error in terms of VK is VK minus YK, purely based on that definition, right? Based on this definition, if you want to get a partial order derivative in terms of VK, it becomes this. Now, once we have those two, we put those two together. If we can define a new, if we put these two together, go back to equation 1, put them back into this equation. Now we have, we can define a new quantity. This is a new quantity, which is if you use this times that, and then if I use this portion, the first two component times this portion, we define this as a Kasiki. Then we can see that we can use negative eta times Kasiki, and then times this VH becomes our delta WHK. If I have delta WHK, I would be able to update my W. Okay, so that's really the idea, you know. So the error from the output layer can be backpropagate to be leveraged for our weight update. Once we calculate the errors due to the input from the hidden layers, we can calculate the errors due to the input from the previous layer. In this case, previous layer would be really the output, right? Instead of going this way, we're looking at this way. So let me give you a direction. So our neural network is doing that, going from input to output. But on the other end, our propagation algorithm is going from the back to the front. That's why we call it back propagate. And then you do that and until the actual input UI. As you adjust all the W's by doing the back propagation, you are able to come back with your corresponding UI so that you can fix your W. Because the objective essentially is trying to minimize that error term, but by doing what? By adjusting our weights. Once you get all of the weights, then you essentially got the, not only get the structure of the model, but also get the corresponding numeric values of the relationship. Okay. Now, we want to expand a little bit on the loss function. We know that what we just said was L2 norm being an objective function, but it can be a lot of different flavors of the loss function. So we did only discuss L2 norm so far, but many other loss functions are used in literature. One of them, you can see that, assume that y is a vector of the predicted value of y bar, is a vector of the true value. Suppose that this is our prediction, this is our true, and then LP norm essentially is, L2 norm essentially is this. So just get rid of a half just to make it a little bit easier in terms of the calculation. That's just a simple transformation. The second one is instead of L2 norm, we can use L1 norm based on loss function. L1 norm based loss function. It could also have KL divergence, which we kind of discussed earlier in the semester, which is the combines entropy and the cross entropy for the second term. That is KL divergence loss function. Could have other flavors as well. So one of them is, you can see here, for other applications such as classification use support vector machines, the loss function can be defined as a hinge loss. Its max of 0 or 1 minus yr bar times yr. That's one. The other one is called square hinge loss function. There's many other loss functions, including Tanimoto loss, Chebyshev loss, and Cauchy-Schwarz divergence. And as you can see, each can serve as a different purpose, but with a different emphasis. So you should also pay attention to what type of error loss function that you might be used in your artificial neural networks. So since the minimization of error term norm is the same as half of the error term norm, or error norm divided by n, where n is a positive integer, different formulations of loss functions may include some arbitrary factors for convenience. Just something that you should be aware. Okay, for now, we'll stop here for artificial neural networks, and after that, we'll continue with some optimizer for artificial neural networks, followed by deep learning. Thank you.